Hello everyone, I'm Antoine from the University of Luxembourg, and today I'll be presenting to you OmniLRS, a photorealistic simulator for lunar robotics. This work has been carried out in collaboration with Junnosuke Kamohara from the University of Tokyo. Nowadays, there is a large breadth of simulators. Just to name a few, we can think of the Viper simulation from NASA Ames, or the Dust simulator from NASA JST, or Lunar Sim from PUT Vision. The common point between all these works is that none of them are publicly available, or if they are not open source. Another common point between them is that neither the terrain generation is explained nor how the assets are placed inside the scene, and often these works lack sim-to-real evaluation. Unlike the previous simulators, with OmniLRS we provide all our code open source. What that means is that all the code required to run ROS1 simulation as well as ROS2 simulation or automated data annotation is fully available. In these figures you can see on the left our real Lunar lab and on the right our digital twin that's available to be used. Similarly, all the code required to generate procedural environment is fully available. On the left, for instance, you can see Thomas cluster point processes that are being used to spawn rocks on the terrain. On the right, you can see the generation of random terrains using our procedural algorithms, and these are inspired from the one available in Pango's. In addition to these, our simulator provides bindings to enable changing the environment through ROS. In the videos shown on the left, you can see the user manipulating the position of the light source. On the video to the right, you can see the user manipulating the position of the rocks. In addition to these methods, others are available, such as randomizing the terrain shape, or for instance, changing the position of the Earth on larger scenes. To evaluate the realism of our simulation, we first generated a synthetic dataset inside our digital twin of the Lunar Lab. In this dataset, we labeled the rocks and terrain through Replicator, a tool that's provided inside IsaacSim. We then collected RGB and depth data as well as distance segmentation and bounding boxes of rocks and terrain objects. In the videos, you can see how that process is done. Then, once this dataset was generated, we manually annotated data from rovers driving around our real facility. In addition to that, since our lab is not a perfect depiction of real lunar environments, we also labeled images from real lunar missions. Using these datasets, we could then evaluate how well models trained in simulation fared on real data. On top of that, we also tested different variants, such as fine-tuning the model on real data after training it on simulation data, or seeing the impact of the different renderers available inside IsaacSim. When performing zero-shot transfer, models trained on simulation data only are not performing as well as models trained on real data. These can be explained by various factors which we'll explore later on. In the videos, you can see on the left the models trained on real data and on the right the model trained on synthetic data. In practice, the model trained on synthetic data is not as accurate as the one trained on real data, and you can see that sometimes doing some misclassification, or it's also missing smaller rocks. However, when fine-tuning models trained from simulation with 30% of the real data available for training, the performance of these detectors surpasses that of the models trained purely with real data. On the left video, you can see the models trained on real data, and on the right, the ones that were fine-tuned. It can be seen that the latter ones are more accurate and less prone to errors. Overall, while these preliminary results are encouraging, this simulator can still be greatly improved. Most notably, models trained on simulated data still struggle to generalize well to real lunar images. This is due to numerous factors such as low texture quality, lack of diversity in our rock assets, or the quality of our terrains. Another issue is that as of today, we do not provide many robotics demonstration tasks, and the size of the terrain that are simulated are constrained to a couple hundred of meters. This limits the usage of our simulation to test SLAM algorithms or long traverses. In the current state of the simulator, some of these points have already been addressed. For instance, the rendering of very large-scale terrain is now possible using our own implementation of geoclip maps for Omniverse. These will enable long traverses of multiple kilometers to be simulated in a single shot. For instance, the image on the left shows the whole lunar South Pole being simulated. The image on the top right shows the ridge of the center crater, while the image on the bottom right shows how the geoclip map decimates the mesh resolution as we move further from the center. Also, in an effort to improve the quality of the textures used inside our simulation, we collaborated with Polyhaven. Together, we went to the Moon Rostock, a lunar analog facility with regolith simulant, to create science-grade regolith textures using photogrammetry. Finally, we have also been working on introducing improved thermomechanics inside our simulator. On the images, you can see a rover dynamically leaving prints inside the terrain. We plan on using this feature to test visual SLAM techniques and see if they can leverage this phenomenon to improve the localization of robots on the Moon. Thanks a lot, and you can find our simulator and code using the QR code or the link below.